Hi, and welcome to Always Eclectic Stacy. This is Always Eclectic Chemistry, and today we're learning the properties of ionic bonds. Ready, set, let's chem! Hi, welcome to Always Eclectic Stacy. Today we're going to be talking about ionic compounds and their properties and a brief introduction on what they are. So, ionic compounds are chemical bonds, and what chemical bonds are a force that holds two atoms together. And for ionic compounds, it's going to be from a positive nucleus and a negative electron, or a positive cation and a negative anion. So when you lose electrons, you become positive. That's a cation because cats have paws, meow, meow, meow. And it might be a negative anion where you're gaining that electron, and that one that's giving and that one that's gaining, they're going to be held together by the electrostatic force. A cation is a positively charged ion. They lose or give electrons to form a stable octet of valence electrons. Please remember that 8 is great, and they're doing this to mimic the noble gas in the row above them. So if they're in row 4, they're going to be mimicking the noble gas in row 3. If they're in row 5, they're going to be mimicking the noble gas in row 4, because they're losing it to get that 8 shells in the outer valence ring. And that is really a noble gas configuration. So the stable octet is the valence electrons is called the noble gas configurations, and the reactivity of metals is based on the ease in which they give up their valence electrons to form a stable octet. If they give them up more easily, they're going to be much more reactive, and if they gain them pretty easily, they're going to be much more reactive. So those with +1 or -1 charges are going to be much more reactive than those with, say, +2 or +3 charges. Negative anions, they gain an electron to form the closest noble gas. So it's going to be forming the noble gas in their same column, or sorry, same row. And again, 8 is great. So they're gaining electrons to fill that outer shell. And the reactivity of nonmetals is based on the ease in which they gain electrons. So column 17 is going to be much more reactive than column 15. There are some rules to the formation of ionic bonds. They can only gain or lose the number of valence electrons. So they actually do lose all of their valence electrons, or they gain as many as they need to get to 8. So for example, columns 1 through 13 and then some of 14 do all form cations. So they lose up to 4 valence electrons in order to form the cation, and they're giving them to an anion. And that anion is gaining as many as they need in order to get to a valence electron of 8. So if you have 5 valence electrons, you need 3 more, 6, you need 2 more, 7, you need 1 more. The number of electrons lost must equal the number of electrons gained. And this is where you get the ratios of valence electrons and how you make ionic compounds with subscripts. So a supercharges cheat sheet is column 1 will form a cation, and it's going to become a 1+ ion. Column 2 is also a cation. It's going to form a 2+ ion. The transition metals and most of column 4, like tin and lead, are cations. They have multiple oxidation states, meaning they can form multiple charges. So those must be provided for you if it's a Roman numeral in parentheses. So remember, 1+ is big I, 2+ is 2 I's, 3+ is 3 I's, and 4+ is an IV. Column 13 is still a cation. It's a 3+ charge. Column 15 is an anion. It's a 3- charge. 16 is an anion. It's a 2- charge. And 17 is also an anion with a 1- charge. Remember that when it's a negative charge, it's gaining electrons because electrons are negative. And so therefore gaining more negative makes it a negative charge, versus the positives are losing electrons, because when you lose a negative, you become more positive. Here's an example through electron configuration. If you look at these electron configurations of both potassium and fluorine, potassium is gaining an electron and fluorine is gaining an electron and potassium is losing an electron in order for them to both look like they're noble gases. Potassium is losing that 4s1 orbital electron so that it goes down to 3s2, 3p6, 2 plus 6 is 8. It's happy. Fluorine is gaining 1 in the 2p5 column so that s1 goes into 2p5, and now they both mimic noble gases and they are happy. And then I showed it in noble gas configuration so that you could see. So some properties of ionic compounds, they're always, this is one of the few alwayses in chemistry, made up of a metal and a nonmetal. And they make something called an ionic crystal. This is the regular and repeating pattern into which the positive and negative ions are packed. There's a ton of different ionic crystal shapes depending on the compound. And this is called a crystal lattice, where each positive ion is surrounded by a negative ion, and each negative ion is surrounded by positive ions. So if you're really thinking about this, it's going to be a very kind of square or structure that's going to have kind of harder edges because it's going to be positive sorted by negative sorted by positives. It's going to be more of a square or rectangular structure than, say, round. It's also really important that it's in this format because it's making a magnet. So the positives are attracting the negatives are attracting the positives, and it's all pulling down into a very tight lattice structure called a crystal lattice, which is a type of ionic crystal. The properties of ionic compounds, their color is related to their structure. So you're going to get a bunch of really different colors based on their structure because of refraction. So the light's going to go through this structure and refract different colors. They have really high melting and boiling points. It's going to be higher dependent on the strength of the lattice structure. The more negative a lattice structure is, the higher the melting and boiling point. And brittleness and hardness is also dependent on the strength of the lattice structure. And the more negative a lattice structure is in strength, the stronger it is. It's important to understand that due to the fact that charged particles must be free to move to conduct electricity, meaning they have to be moving. That's why metallic bonds conduct so easily because you have the delocalized electrons. But in an ionic crystal, they're not free to move, so a solid state ionic compound are non-conductive. Therefore, you get something called an electrolyte when you mix it with water. Yes, those are the things you drink. This is an ionic compound whose aqueous solution, aqueous meaning mixed into water, conducts an electric current. The lattice energy, this is the energy required to separate 1 mole, which is an amount of electrons. And it's easy to understand. We use moles a lot in chemistry because 1 mole of one thing is exactly the same as 1 mole of another. It's the only unit in chemistry that can be directly converted because they're all the same. So we use that a lot in chemistry. So back to lattice energy. It's the energy required to separate 1 mole of the ions of an ionic compound. This is the strength of the forces holding the ions together. So remember I said it was more negative, the stronger. Lattice energy is measured in kilojoules per mole. And so the more negative it is, the stronger it is. So here is some examples. I know these don't have negatives on them. It's assumed that you understand that. But if you look at gallium oxide, it has 15,600 kilojoules per mole. It's going to be incredibly hard to separate that versus rubidium bromide over here that has 660 kilojoules per mole. It'd be very easy to separate that. Thank you so much for watching our video on properties of ionic compounds. If you like this video, please don't forget to check out our other content, and please do like and subscribe. Have a ionic day.